Welcome. In this talk I'm going to go through the Cfl condition. It's the Courant-Friedrich-Leary condition, and it's a very important limit on many numerical methods, in particular explicit time integration methods. So I'm going to show how this works using quite a simple scheme, but the same limits and the same principles apply for much more complicated schemes. So if you haven't seen the previous video on analysing numerical methods with the von Neumann method, I recommend you watch that first, but if not, I'll try and give you some background. So the basic idea is we're trying to solve a relatively simple equation. So we're solving an advection equation. So we're solving a quantity rho, which is a function of time and space, and we're solving in one dimension a fixed velocity u in the x direction, and here we have a d rho by dx. And this is a simplified version of the density equation for Euler's equation. And we're starting with a simple one-sided finite differencing method. And so we write that we essentially divide up space. So here we have the x direction, for example. This is x. We divide up space into points. So xn labels that one, xn minus 1. And then we approximate, so d rho by dx is approximately rho at xn plus 1, so that's this, so xn plus 1 here, minus rho at xn, divided by delta x, which is the spacing between these points here. So here's delta x. And it's just essentially drawing a straight line between these 2 points to calculate a gradient. And so this is the gradient, which we're going to label as the gradient at xn, is approximated like this. We saw previously this is a first order method, so there's an error which is proportional to delta x. Okay, so in that previous video I showed that this gives some limits on the directions. In particular here ux should be negative, so that the flow is from right to left. Otherwise, if you have a flow reversed, then we have an unstable situation. In the previous video I assumed that this time integration was perfect, and so I had no approximations here. This video we're going to look at how you solve this, how you integrate the system in time. And I'm going to start with the simplest method, which is the first order method, so the same scheme as this. So we write that d rho by dt is again approximately, so rho at t. I'm going to call the time index j. So space index n, time index j, so it's j plus 1, minus rho at tj. So it's the same principle, we're dividing up time into points. So tj is the jth time index. And then here we have a delta t instead of a delta x. It's the same, so it's the same equation, so we'll have the same kind of error, so order delta t. Have an errors term which is proportional to delta t and the delta t squared and so on. So if we put this into this equation, so this equation here, we can write down essentially a finite difference formula for this equation, and it will contain terms involving rows at different x locations and the value at rho at the next time point. And if we wanted to, we could rearrange this equation to work out what the value at the next time point was. And so we could use it to integrate the system in time. For now, we're going to use this to analyze the equations. And so we have, well, I'll write this out here. So we have rho at t at j plus 1 minus rho at tj divided by delta t is minus ux. And then we have a rho at xn plus 1 rho at xn divided by delta x. Now I haven't, on this left hand side I didn't put the space indices, so all of this side here, this is all at xn, and this is all at tj. So you could put an xn in both of these and a tn in those, just make it a bit shorter. Okay, so then we're going to apply the von Neumann analysis method. So von Neumann's method. The idea here is that we put in essentially a trial solution for what rho looks like. So we say that rho is some function of x and t. So here I'll just put explicitly time and x, has some kind of amplitude a, which is just a function of time, and it has some kind of wave-like behavior in space. So okx. So it's basically a wave in space, so x, and it's essentially growing or shrinking or staying constant amplitude in time. And so if the amplitude is increasing in time, then we have an unstable wave, and we'll get numerical problems. And so we'll find if a is constant or decreasing, then the method is stable. And so we essentially substitute this expression here into these formulas here. And so we end up with the difference in time gives us an a at t j plus 1 minus amplitude at t j divided by delta t. And both of these points were at x index xn, so this gives us an e dik xn. And then we have the right side, we have the ux term, and then we have the right hand side is all at tj, so this gives us an amplitude at tj, and then we have the difference in space, so this gives us an e to the I ik x n plus 1 minus e to the ik x n divided by delta x. And then we can rearrange this a little bit, and we can use the fact that that x n plus 1 is equal to x n plus delta x, and so e to the ik x n plus 1 is equal to e to the ik xn times e to the ik delta x. So just adding on, so just split this up and split that term out. So xn plus delta x gives us this xn plus 1. And we can divide through by a at tj and multiply through by delta t, and we sort of group these terms together, and we end up with essentially a term which looks like, so we have a at t j plus 1 minus a at tj. We divide through by a at tj, and then we move this delta t over here and group together, so we have a delta t times ux divided by delta x. Ux delta t over delta x. We have this e to the ik xn, which cancels out of both these terms here. So this term just gives us an e to the ik delta x. So we have an e to the ik delta x from this term here, minus this just cancels to 1. So this term here and this term cancel out. And so now we can write what we want, which is essentially finding out how does the amplitude at the next time point depend on the amplitude at the previous time point. So we have a at tj plus 1 over a at tj equals, and then this is just 1, so a at tj divided by a at tj. Move over to the other side, so this is 1 minus ux delta t. Okay, delta x minus 1. Okay. So if this is greater than 1, then that means that the amplitude at the next time is bigger than the amplitude of the previous time, and we have a wave that's growing in time. And so this must be less than or equal to 1 for stability. And so we can calculate what this will be. This quantity here, this we'll label mu as the Courant number. And it's an important quantity. This turns up all over the place when you try and calculate stability of numerical methods for things like wave equations. So any hyperbolic kind of equations, this term appears. So it's essentially the ratio of the distance travelled in a time delta t, so this is the velocity times the time, because of the distance the wave travels, divided by the size of the mesh spacing. So it's like how many grid points does the wave travel in the time delta t. Okay, and then we can essentially write this using, by turning this into sines and cosines. That makes things a little bit easier. Except what we've ended up with here is this is actually complex. We have a real part and an imaginary part. So so here a t can be complex. So it can essentially change the phase of the wave, and so this means that essentially we have a phase difference, but what we care about is the amplitude. So for stability, the amplitude is important. So we just care if the wave is growing or shrinking. We don't necessarily care about the phase at this point. Although the phase is important because it will change how the wave propagates. So the speed of the wave in the simulation can be different from the speed of the wave in the physical system. What we'll do for now is we'll calculate the mod squared value of this, so this times its complex conjugate. This will make things easier for the analysis. So we have a tj plus 1 over a at tj modulus squared. And then we'll multiply this thing out here. Now here we have a 1 minus mu ik delta x, ik delta x minus 1, and then multiplied by its complex conjugate, so we have a 1 minus mu e to the minus ik delta x minus 1. Okay, then we just multiply these terms out, so we have a 1 beginning, so then group together terms with a single power of mu. So we have mu, so we get a term from here. So this gives us an e to the I ik delta x. We get a term coming from here. Delta x, and then we get this term here. Okay, and then we have terms involving mu squared. So here we have mu times mu, so I guess gives us a plus mu squared. And then we multiply these brackets here, so we just have a e to the ik delta x minus 1, and then e to the ik minus ik delta x minus 1. And then this bracket here is essentially 2 minus k delta x. So this is essentially the same as this bracket here with a minus sign. And so we can say that we have so 1 plus mu squared times this minus mu times this. So we can simplify these terms here. So we have an e to the ik delta x and an e to the minus ik delta x. And we can use that e to the I ik delta x plus e to the minus I k delta x is 2 cos k delta x. And so this term just becomes minus 2 cos k delta x. And so we can just write that mod a tj here, mod squared, and here we just group together, so we have a 1 minus, and then we have a mu minus, a mu here, and then a minus the mu squared, so here we get a mu plus mu squared times this. This was a 2 cos k delta x minus 2. And so we just take the factor of 2 outside, we'll have a 2, and then we have a cos k delta x minus 1. Okay, so now this quantity here, so cos minus 1, so this is always less than or equal to to 0. So the most that cos can ever be is 1. So this can at most be equal to 0. So this is always negative. This has a minus sign here, and so if this is negative and this has a minus, then this must be negative. So if this is positive, then this whole thing is bigger than 1, and we have a growing wave. So therefore, we must have that mu plus mu squared must be less than or equal to 0 for stability. Because if it's bigger than 1, then this is larger than 1, and the wave is growing. So there's a few cases where this is unstable. So where is this unstable? So the first case is, of course, if mu is bigger than 0, therefore then it must be unstable. And mu is, if we just write down, so mu is equal to, so it's ux delta t over delta x. And so if the velocity is positive, if ux is positive, then this is unstable. And this is just what was shown in the previous video, that u has to be negative for this to be stable. So ux must be less than 0 for stability. And that has nothing to do with the time integration. This was just to do with the spatial method that we're using, because we're using a one-sided difference, and the difference is going to the right. The wave has to be moving to the left, or it would be unstable. So if you used a different finite difference method for space, then this would not be the case. So the second case where this is unstable is if mu is less than -1. So if mu is less than -1, then this term becomes larger than that term, and again it becomes positive. And so therefore, mu has to be larger than -1 and less than 0. So it has to be within those limits. So this condition that mu must be less than 1 is essentially a restriction on the modulus ux delta t over delta x must be less than 1. And this is the Cfl condition. So this condition here, that essentially you can write it several different ways, but one way of writing it is that basically delta t. So if you see it as a restriction on the time step, so delta t must be less than delta x divided by ux with a modulus sign, because ux could of course be negative. So this is the Cfl condition, and it's a limit that most numerical schemes, so that all explicit methods, suffer from this problem, that if you have fast waves in the system, so if ux is very large, then you have very small time steps. There are other schemes called implicit methods or semi-implicit methods, which try and get around this limit, but they have problems of their own. So this is quite an important limit in numerical methods.